So, lesson 4.3 is all about derivatives and what they tell us about a graph. And some of this should be reviewed because we talked a little bit about it in, I want to say chapter 2, but so let me just take a look here and go. So one of the big theorems is this thing called the mean value theorem. And it tells us if we have a function that is differentiable, in other words, we can take its derivative on the interval from a to b, then there exists a number c between a and b such that the derivative at c is equal to the slope of the line that connects the endpoints. So f prime of c is equal to f of b minus f of a divided by b minus a. It just guarantees that there's a place where the slope of the tangent line is equal to the slope that connects the endpoints, as long as the function is differentiable. So in order to be differentiable, it needs to be continuous. It needs no breaks, no all those fun things, no vertical tangent lines, things like that. So I've seen on the AP exam where they'll say, does the mean value theorem guarantee that that this is true for this given function? And you have to recognize either yes, because it's a continuous differentiable function, or no, because the derivative does not exist at a certain point. Kind of the big takeaway there. All right. So I think we've talked about this a little bit, but we can tell whether a function is increasing or decreasing by a little test. If the derivative at some point c is greater than 0, then the function is increasing. So first derivative is positive, function is increasing. If the first derivative is negative on an interval, then f is decreasing on that interval. So basically what we will do most often is find where the first derivative is 0 and then look at the intervals that breaks our function into. And so we'll say, oh, it's increasing on this interval and decreasing on this other interval. So let's take a look. Where is the function 3x to the 4th minus 4x to the 3rd minus 12x squared plus 5 increasing, and where is it decreasing? All right, so first step, take the derivative. What is the derivative of 3x to the fourth?
Twelve x to the third.
12x to the third. All right, minus the derivative of 4x cubed.
Twelve x to the second.
There you go. Minus the derivative of 12x squared.
24x.
And most importantly, the derivative of 5.
0.
0. All right, good. So to find, again, where this function is increasing or decreasing, I'm going to look at the derivative, and I'm going to start by looking at where the derivative is 0. So I'm going to factor the derivative, and in this case, there is a factor of 12x that I can factor out. And then I can factor that trinomial like so. And using those factors, I know that the derivative is 0 when any of the factors are 0. And so one way that you can kind of organize this is on a number line. So I'm just going to label this number line. This is f prime of x. And I'm going to plot those 3 x values. And what I'm going to do is look at the intervals that those x values break my number line into. So I've got from negative infinity to -1, -1 to 0, 0 to 2, and 2 to positive infinity. And I'm just going to pick values on each interval, plug into the derivative. If my answer is positive, I know my function is increasing. If it's negative, I know my function is decreasing. So I don't even care what the value is when I plug it in. I just want to know, is it positive or negative? So if I pick a number less than -1, like -2, and I'm going to plug that into my derivative, and I'm not going to actually use the factored form of my derivative. When I plug in -2, my first factor, 12 times -2, gives me a number that's negative. And -2 minus 2 gives me a number that is negative. And -2 plus 1 gives me a number that's negative. So if I take a negative times a negative times a negative, my answer is negative. Then I'm going to take a value between -1 and 0, like -1/2. Again, plug it in. If I plug in -1/2, my first factor is negative. My second factor is negative. My third factor is positive. So again, I have a negative times a negative times a positive. So that product is positive. Pick a value between 0 and 2, like maybe 1, and plug in 1. If I plug in 1, I get a value that is positive, a value that is negative, and a value that is positive. So a positive times a negative times a positive, that's going to give me an answer that's negative. And last, pick a value greater than 2, like pi or 3, either way. And when I plug that value in, I get a factor that's positive, positive, positive. So then I can tell where I'm increasing or decreasing just by reading off of that number line. So we are increasing on the interval from -1 to 0. And so I'm just going to use interval notation. We are also increasing on the interval from 2 to positive infinity. We never include the endpoints because at -1, at 0, at 2, our function is not increasing or decreasing. It's holding steady just for that split second that it's at those values. And then for decreasing, it's decreasing everywhere else. So increasing where the derivative is positive, decreasing where the derivative is negative. All right, and that leads us to this thing called the first derivative test. So suppose that C is a critical number of a continuous function f. So just a reminder, a critical number is a number where the derivative is 0 or undefined. If the derivative changes from positive to negative at C, then f has a local maximum at C. So we're talking about f is positive. I'm sorry, f prime is positive. So that means f is increasing. It gets to C and then it starts to decrease. So that gives us a local maximum value. If f prime changes from negative to positive at C, then f has a local minimum. Again, f goes from negative to positive. So when f prime is negative, I'm gonna restate that because I misspoke. F prime changes from negative to positive. So that means f goes from decreasing, gets to C, and then starts to increase. So we get a minimum value. There is a third thing that can happen, and that would be if f prime does not change signs at C. So f prime goes from positive to positive or negative to negative and just has that value at C where the f prime is 0, then we don't have a minimum or a maximum. All right, the next thing we will look at is concavity. Um, concavity deals with the shape of a function. It's not that thing that the condentist goes and fixes in your tooth. All right. Concavity is based on the second derivative. And if the second derivative is positive for all x on some interval I, then the graph f is concave upward. And concave upward is shaped kind of like the letter U. So a parabola is concave upward. If the second derivative is negative for all x in some interval I, then the graph of f is concave downward on I. And concave downward has a shape kind of like the N. So that's one way that I try to remember it. Concave up is U-shaped, concave down is N-shaped. So more or less. So we had the first derivative test that we could use to find excuse me, if we had a minimum or a maximum value. There is also a way to do it with something called the second derivative test. So again, we're going to assume that our second derivative is continuous near a value c. If c is a critical number of the function, so the derivative at c is 0, and the second derivative at c is positive, then we have a minimum at c. So its first derivative is 0, and we're concave up. So if you think about a parabola, the vertex would be at c, and that would be a minimum value. Kind of opposite of the way that seems right, because we have a positive second derivative, but a minimum value. If the first derivative is 0 and the second derivative is negative, then we have a maximum value because it's concave down. And yes, if you were asked on an AP exam to find local minimum and maximum values and justify whether it's a minimum or a maximum, you could, if you knew the first derivative and the second derivative, you can use your justification being the second derivative test. The point where the curve changes its direction of concavity is called a point of inflection. And so if our second derivative is 0, that would be a possible point of inflection, and we'd have to look similar to the way we did with our first derivative for increasing and decreasing. We could do the same thing with our second derivative and talk about where it's concave up and concave down and where the points of inflection would be. I am not going to show this video. It's actually quite entertaining, but if you want, you can certainly look it up. I believe you can find it on YouTube, Theorem of the Mean Policeman. If we were in class, I would definitely show it. But because we're not, I'm gonna spare you the 20 minutes of that video. So 2, 7 through 9, 20, 21, 29, and 30. For 21, 29, and 30, skip part D, you don't have to do it. On Thursday, there will be that review assignment. I will put that out. And then next week, you'll have the quiz, the first half of the week. Monday's class, obviously we'll have to be there for attendance purposes. The only thing that we will do on Monday is I will answer any questions on the review that you want to ask.